Welcome to the Explainer. Every single piece of tech you use, your phone, your laptop, it's all running on a set of hidden rules, a kind of secret contract. And today, we're going to decode that contract because it explains so much, not just the speed of your devices, but even why some of the most powerful video game consoles ever made just completely failed.
Okay, so to really get this, we're going to jump in the time machine and head back to the mid-90s, right into the middle of a classic console war. I mean, this was a huge moment. Gaming was making this massive leap from flat 2D sprites, think Super Mario, into this wild new world of 3D polygons. All right, so in one corner, you've got the Sega Saturn, and let me tell you, on paper, this thing looked like an absolute beast. We're talking not one, but two main CPUs, and on top of that, 6 other specialized processors. It was just packed with silicon. Then, in the other corner, you have the new kid on the block, Sony's PlayStation. Its design was, well, a lot more focused, just a single main CPU, but it had this special engine built from the ground up just for 3D graphics.
But here's the thing, right? Raw power, it isn't everything. For all those impressive specs, developers started saying that programming for the Saturn was just a nightmare. They were really struggling to get all those different processes to play nicely together. And because of that, a ton of the games just couldn't unlock what the machine could really do.
And that brings us to the big mystery. How could a machine with a whopping 8 processors struggle against a competitor with a much simpler design? Well, the answer? It gets to the very heart of how all our digital devices, every single one, actually works.
See, it all comes down to this crucial and kind of invisible layer. You can think of it like a contract, a deal made between the software, your games, your apps, and the actual physical hardware, the silicon chips doing all the work. It's called the Instruction Set Architecture, or ISA for short. Basically, it's the official language that software uses to talk to the processor. It's the rulebook. It defines every single command the hardware can understand. And this creates this really clean separation. So the software programmer doesn't have to worry about all the messy, complicated physical details of how the chip is actually built.
Now, before the ISA became a standard thing, it was the Wild West. Total chaos. Every single computer had its own unique hardware. And that meant programmers had to write code for one specific machine. Imagine writing a book that only one person in the world could ever read. If a new computer came out, you had to throw all your work away and start from scratch. The ISA, it changed everything.
But here's where it gets really interesting. This contract isn't just written one way. Turns out there are 2 totally competing philosophies on how to design it. And this rivalry, this debate, has pretty much shaped the entire history of computing as we know it.
Okay, so on one side, you've got CISC. That stands for Complex Instruction Set Computer. Think of this as the Swiss Army knife approach. One single command can do something really powerful, like a multi-step operation all at once. Then on the other side, you have RISC, Reduced Instruction Set Computer. This is more like having a small set of very simple, very specialized tools. Each command just does one tiny thing, but it does it incredibly fast. So what's the better choice, right? The big, powerful, all-in-one tool, or the set of simple, lightning-fast ones?
And you can really see the difference right here. Look at this. To do a single, kind of complex task like adding 2 numbers from memory, a CISC chip, like an Intel x86, might do it all in one single instruction. Boom, done. But to do that exact same thing, a RISC processor has to break it down into a whole bunch of simple steps. Load this value, now add this to it. Okay, load that other value, add them together, now store the final result. It definitely looks like more work, right? But the whole philosophy behind RISC is that each one of those tiny steps can be executed by the hardware at blinding speed.
So, okay, this isn't just some abstract, nerdy debate for chip engineers. These 2 philosophies, CISC versus RISC, have had massive, real-world consequences. I mean, they've literally defined the entire ecosystems of the gadgets we use every single day.
So let's talk about CISC. Its complexity had one absolute killer feature: backward compatibility. Because the instructions were already so complex, guys like Intel could keep adding new features to their chips, while making sure the new processors could still run all the old software. And that was everything. It created this gigantic library of software that just worked, and that's what cemented the x86 PC's dominance for decades.
But then, the mobile revolution happened, and the game completely changed. All of a sudden, it wasn't about raw power anymore. It was about power efficiency. You needed a battery that could last all day. And the simple, efficient design of RISC, especially the ARM architecture, was absolutely perfect for that. The result? A complete and total takeover of the mobile world. Yep, that simple, efficient RISC contract is almost certainly the thing powering the phone in your pocket right now.
Okay, so now we can finally circle back and solve the mystery of the Sega Saturn. You see, the problem wasn't that its RISC processors were bad. Not at all. The problem was that the contract Sega wrote for them was an absolute nightmare. It forced developers to manually split up tasks between two main CPUs that, get this, didn't even talk to each other easily. Then they also had to manage two totally separate graphics chips at the same time. And, this is the real kicker, they had to do all of this with almost no help from the console itself. The PlayStation gave developers a helpful set of software tools, a BIOS, to make life easier. The Saturn pretty much didn't. So in the end, Sega gave developers a box of simple RISC tools, but then handed them this ridiculously complex blueprint with no instructions. It was a recipe for disaster.
And look, this isn't just a fun story about retro gaming. This hidden contract, this constant negotiation between what the software wants to do and what the hardware can actually deliver, it shapes your digital life every single day, and often in ways you would never, ever expect.
Just think about loading screens. I mean, what is a loading screen? It's the most obvious sign there is that the hardware is struggling to keep up with what the software is asking for. And game developers, they've become absolute masters of illusion, finding these really clever ways to hide the limits of that hardware contract. And that's maybe the biggest lesson here. The most powerful hardware doesn't always win. A lot of the time, the hardware that's just easiest to work with is the one that comes out on top. You know that famously long elevator ride in the original Mass Effect? Yeah, that wasn't just for dramatic tension. It was a loading screen in disguise. It was literally just buying time for the hardware to pull the next level off the disk. Or how about the Animus Void in Assassin's Creed, where you can run around in that white space? Yep, same exact idea. These are just brilliant software tricks designed to make you totally forget about the physical limitations of the box you're playing on.
So all of this leaves us with a pretty big question for the future. Right now, we are on the edge of entirely new ways of computing. We're talking specialized AI hardware, cloud gaming where the processor is miles away, even quantum computers. And every single one of these is going to need a fundamentally new contract, a new ISA between the software and the hardware. So the next truly huge leap in technology, it probably won't just come from a faster chip. It's going to come from whoever writes the smartest new rulebook.